All right, Chem 11, we are back. Our next lecture is the lead-off batter in a lineup of lectures that are going to deal with something incredibly important in our course, and that is determining the names and formulas of the various chemical compounds we're going to come into contact with this year in grade 11 chemistry. All right? The ability to determine the name or formula of a compound is the #1 skill you must have in any chemistry course, Chem 11 included. All right? You know the poster in my room, stuff you got to know. #1 on that list, compound names and formulas. All right? So today we're going to start that super important lecture. If you don't understand something that I go over today, you got to let me know. You got to reach out to me. All right? You can't afford not to know this stuff. All right? So let's go forward. All right? As usual, we have up here in the corner, that's our iPad with the PowerPoint lecture note that you can download from the D2L site for our course. And then we've got the whiteboard here that we will be, obviously today working at the various names of compounds on. All right? Today we're going to be focusing in on binary ionic compounds. Now our note, it actually has all the compounds in it. I put it all into one. But what we're going to do is we're going to learn it chunks at a time. So the first chunk, or episode, are the binary ionic compounds. All right? So you might be asking, who makes up these names? Like, where do the rules come from? Well, there's an organization called IUPAC. IUPAC. IUPAC is an acronym for the International Union of Pure and Applied Chemistry, and they're the ones that come up with all the names and formulas. And there's a system or a set of rules that they use worldwide, right? You can imagine if you discovered a drug that could kill cancerous cells, the cure for cancer. You would want that formula out there around the world as quickly as possible. So if all chemists on Earth use the same rules and regulations for naming compounds and writing their formulas, then that just eliminates language barriers, and that cure for cancer can get out there even quicker, right? It's like in biology. We have scientific names for all the species. So all the local names and all the different dialects or languages, they may not mean anything to someone outside of that language or dialect, right? Our word for dog is not everybody's word for dog, right? But the scientific names are known by biologists worldwide. So for example, we are Homo sapiens. If I go to any country in the world and say I'm doing a study on Homo sapiens, they're going to know it's us, it's humans, right? Felis domesticus, that's your cat. Canis familiaris, that's your dog. You get the idea. So this system eliminates language barriers and problems of communication, so we can streamline it and share information as quickly as possible. I'm just going to bring this all up so that we can go through it and I won't have to be reaching out across all the time. So, a binary ionic compound. What is a binary ionic compound? Now the word binary means it's just two elements. And as we learned before, an ionic compound is a metal and a non-metal combined. So here's our metal and a non-metal element, all right? And as we talked about when we did chemical bonding, metals, in terms of electronegativity, or the ability to fight for electrons, they're pretty wimpy. Their electronegativity values are very low. So here's Wimpy Kid. He represents our metal. And then we've got the rock. You knew he wouldn't be away for very long. The rock is our bully. He's our non-metal. So a binary ionic compound has a metal and a non-metal, just two elements. And as we know, what's going to happen? Well, in that quest for the stable octet, the electron from the metal is going to end up being put over here on our non-metal. The non-metal is so much stronger, so much more electronegative that it just steals that electron away from the metal. What happens then? Well, we get the formation of an anion, which is the negative ion, and the formation of a cation, which is the positive ion. And because we've got one positive ion and one negative ion, they stick together. All right? Now, we have to represent both elements in the name. We have to represent the metal and the nonmetal. So these compounds, ionic compounds, will have a first and last name just like you. Right? Here's the rule. When you have an ionic compound, the positive ion goes first in both the names and the formulas, followed by the negative ion. All right? So what that means is our positive ion, the cation, the metal goes first. The metal will go first in the name, and it will go first in the formula. And that will be followed by the nonmetal. Right? So, let's take a look at a common example here. All right? Sorry guys, you gotta go. I'm sure The Rock will beat me up later for doing that to him, removing him from the slideshow, but it's gotta be done. Sometimes The Rock has to know his role and get out of the way. All right, so here's potassium, here's fluorine, and we know what's gonna happen. This electron's gonna go over to here. Fluorine's the bigger bully, right? Potassium is our metal, and fluorine is our nonmetal. The metal is going to form the positive ion. The nonmetal is going to gain that electron and form our negative ion. You've seen this before in the bonding slideshow. So, if we were to name this ionic compound, here's how it works. We're going to actually just name the metal as it is. So the name of the metal is potassium. Now, the nonmetal, something happens to the name of the nonmetal, and what we do is we get rid of this ending on the nonmetal, and we put IDE. IDE tells us those two elements are together. All right, so it's not just a random list of elements. So, what does that mean? Well, our fluorine now becomes fluoride, right? That IDE ending tells us potassium and fluorine are together. When I say potassium fluoride, any chemist is going to know, oh, you're talking about that. That's KF. There's our positive ion first, positive ion first. The negative nonmetal ion second. The negative nonmetal name second. So, that's all that's to it. The name of the metal does not change. The name of the nonmetal we shorten, so we cut off the end and we put "ide." So an easy example, potassium fluoride. All right? Now, let's do a few more examples of these. This is pretty easy stuff, right? Nothing here that you haven't seen before in grade 10. So the examples on the slideshow, we've got K2S, NaCl, and Mg3N2. All right? K is potassium. I do not change that name. The name of the metal stays. Potassium. Sulfur. Sulfur is going to become sulfide. All right? I'll do sodium in a different one. So there's a different color so we can tell it apart. This next one, sodium. I don't change the name of the metal whatsoever. And chlorine becomes chloride. And this one we'll put down here for the sake of space. The metal stays the same. It's simply magnesium. Don't change that metal name. Nitrogen, I'm cutting off a lot of the end of this one. It just becomes nitride. All right? Pretty easy stuff. There's that IDE ending on the nonmetals. And again, if we swipe, like we say in class, if it's on the internet, it must be true. All right? Now, there are some things called transition metals. All right, transition metals are the D block, right? Remember we talked about S block, P block, D block, F block, right? On our periodic table, this is the D block, all this middle area in here, right? Remember doing SPDF orbitals. Now, a lot of the metals in there have more than one charge. And what their technical name is multivalent metals. All right? In grade 10, these are the 4 multivalent metals that we had to know off by heart. Copper, iron, lead, and tin. Copper could be a 1+ or a 2+. And I know these all have to be positive charges because the metals lose electrons, which leaves them positive, right? The protons didn't change. So copper, iron, lead, and tin. Copper, 1, 2. Iron, 2, 3. Lead could be 2 or a 4. Tin could be a 2 or a 4 as well. And these were the positive ionic charges that these 4 metals could have. Now, we still have to know these 4 off by heart. But the question usually comes up, is there more than just those 4? And the answer is certainly yes. There's a bunch of them. So I have a periodic table that I downloaded from ScienceGeek.net. Giving a shout out to ScienceGeek.net here. And you can see this periodic table focuses on ions. So here's our D block in here, and you can see even down here in the F block there are some multivalent metals as well. So you can see the blocks that are cut in half, they have multiple valencies, multiple possible ionic charges. There's iron, there's copper, lead, and tin, but you can see there's titanium, vanadium, chromium, manganese, cobalt, nickel, palladium, platinum, mercury, gold. They're all multivalent, right? And there are a few that aren't. You can see zinc, cadmium, and silver only have one particular charge, right? This table is very useful. Again, you can get it at ScienceGeek.net. If you put in printable periodic table into Google, look for the link that comes up that says Science Geek. It'll be one of the first few links. A great site with a ton of printable periodic tables. That same site is where I got this periodic table that we use. Now, of course, I've written on it, but you get the idea. This is also a Science Geek printable periodic table. But this one's awesome. So I would actually maybe print this one off and keep it in your binder. You can see a lot of the polyatomics that we're going to be using later on are on it as well. All right? So when we name these things, we have to name the metal, obviously. So copper, iron, lead, tin. But we also have to indicate what form of it is. Is it copper 1 or copper 2? Is it lead 2 or lead 4? Right? So what we do is we use Roman numerals, right? You should remember this from grade 10. So it's going to be copper 1 oxide or lead 4 chloride, right? So when we have to name these things, we have a first and last name because, again, there's 2 elements. The first name is the name of that multivalent, or as I say, shifty metal. Shifty meaning, well, one copper is 1 and the other one's 2, and sometimes lead is 2 and sometimes it's 4. So it's kind of shifty that way. So the name of the metal followed by the Roman numeral, which indicates the charge on that metal. All right, it's got to be a Roman numeral. They're pretty easy. We don't go anywhere past 4, I don't believe, for grade 11. The second name, again, is the name of the non-metal, only we cut off the end and we add that IDE. So it just doesn't appear to be a random list of elements. That IDE tells us they're together. All right? So here are some examples here. All right, I'll write these down quickly. our first example, Cu3N and SNO2. All right, I'll do this one first. So if I had to name this, I look at it and go, well, Cu is copper. And then I go, wait a second, copper shifty, I got to put a Roman numeral in there. And nitrogen becomes nitride. Now, how do I get that Roman numeral? I'll show you. Now, here's where it can get kind of iffy. I know a lot of teachers say, oh, do the reverse of the crisscross, all right? And in some cases that will work, right? And what I mean by that is, and I'm hesitant in showing you because I don't want everyone to do this, I want us to do it a different way, but teachers will say, oh, well, there's a 1 here, reverse a crisscross, it's copper 1. And that will work quite often, all right? That's gonna work probably 70% of the time, right? But you don't want to be right 70% of the time. You want to be right 100% of the time. So what we're going to use is something called the zero-sum rule. All right, what the zero-sum rule says is all of your positive charges in a compound have to balance out or neutralize or cancel out all of the negative charges. All right, and that's called the zero-sum rule. Zero-sum rule. All right, that means that your positive charges have to cancel out or be equal to your negative charges. All right, so let's take a look at copper 3 with the N here. Let's use this rule. Now what I have to find is the charge on my copper. So I'm going to put a little question mark there. And then I'm going to go with what I know. I know I have 3 coppers. I also know that I have 1 nitrogen, right? Even though there's no 1 there, I know there's a 1. They wouldn't have written N if there wasn't a 1. Now, I know the charge on nitrogen, right? Remember this, right? 1, 2, 3, 4, 3, 2, 1, 0. These are the ionic charges that we worked out earlier in the year. And here's nitrogen right there. It's a 3. So I'm going to put that 3 up here. It's a 3 minus. Now I multiply this side. 1 times 3 minus is 3 minus. So if I have a 3 minus here, it has to be equal to 3 plus on the other side. So on this side, when I multiply these, it has to equal 3 plus. Well, 3 times what is going to give me 3? Well, it's going to be 1. And so it's copper 1 nitride. All right? Now, let's do the second one. The second one, I guess I'll do in blue. All right? Now, I see this. Give me the name of that. Well, I know it's going to be tin, something, and not oxygen, but oxide, right? That IDE ending. Now, I'm going to rewrite this here down below. This is like my scrap paper down here. And again, I have to find the charge on the tin. So let's go with what I know for sure. You know, go with what you know. I know I got 1 tin. I know I've got 2 oxygens. And I know the charge on oxygen is a 2. Right here, oxygen 2. 2 times 2 is 4. And we know since oxygen is the negative ion, it's 4 minus. So if this side is 4 minus, it means the other side has to be 4 plus. 1 times something gives me 4. Well, that's easy. It has to be 4. 4 in Roman numerals is IV, which literally translates into 1 before 5, which is what 4 is, right? It's the 1 before 5. So again, oxygen's charge is 2 minus. 2 times 2 is 4. If this side is 4, this other side must be 4. 1 times something gives me 4. Well, it's got to be 4. Over here, 1 times 3 gave me 3. The other side also has to be 3. 3 times something gives me 3. Well, 3 times 1. And so I put the Roman numeral 1 in there. Easy enough, right? Not too hard. Now, if I look at this, let's say we went with that reverse crisscross rule. right? We know the real name is tin 4 oxide, but if I reverse a crisscross and brought that 2 up here, I would say it's tin 2 oxide, and that's incorrect, right? Because remember, when you do the crisscross rule, the crisscross method to make up these formulas, one of the steps is reduce. So every time you have to reduce, it kind of ruins that reverse the crisscross thing. If you go with what you know and you use the zero sum rule, you'll get it right every time. Do you want to get it right 100% of the time, or do you only want to get it right 70% of the time? All right, let's do a couple more and then we'll call it a day here. I'm going to keep that up just because it's helpful. So let's go with SnCl4, and let's go with Fe2O3. All right, let's do pink here. All right, I know this is going to be tin something chloride, right? The ID ending, not chlorine. So scrap paper, boom. I rewrite this on some scrap paper, right? I'm looking for this right here. I'm looking for that charge. So go with what I know. I know I've got 1 tin. I know I've got 4 chlorines. I know the charge on chlorine is 1 minus. Let's double check that. There's chlorine, it is 1 minus. All right. 4 times 1 is 4. That side's minus. That means if this is 4, right? 4 minus means the other side's got to be 4 plus. So this is 4 minus. This side has to be 4 plus. 1 times something is 4. Well, it's got to be 4. So the IV goes there. Let's do our next one here. I'll do it in blue. Fe2O3. I write down the name. Iron. I know iron is shifty, so I got to put a Roman numeral in there. Oxygen becomes oxide. All right. Go to my scrap paper. Rewrite the formula. Fe2O3. And I go and say, okay, I have to find that charge right there. Question mark. Go with what I know. 2 irons, I know I got that, and I know I got 3 oxygens. The charge on an oxygen is 2 minus. 2 times 3 is 6. If this side is 6 minus, the other side has to be 6 plus. So go over here, 6 plus, to cancel that out. 2 times what gives me 6? 2 times 3. This is iron 3 oxide. All right? So basically what we're doing is we're using the negative side to figure out the charge on the positive side, right? We use the chlorine, this negative side, to figure out that this was a 4. We use this negative side to help us figure out that this was a 3. All right? And that's it. Now, polyatomic ionic compounds we'll do next day. Taking baby steps, a little bit at a time. Hopefully everything made sense today. Binary ionic compounds, just 2 elements. Sometimes that metal is shifty, but now you know. If you have any questions, comments, or concerns, leave them below this video in the comment section on YouTube, or if you're in my class, reach out to me using EDSB or whatever other methods, or raise your hand in class. Anyway, that's it. I hope you understand, and hope you understood, and we'll see you around. All right, bye-bye.